the impossible is happening right now beneath your feet. As 3I Atlas races past our planet at 60 kilometers per second, this massive interstellar visitor isn't just passing through our cosmic neighborhood, it's fundamentally disturbing Earth's deepest structures in ways that NASA scientists are calling geologically unprecedented. Ocean levels are rising faster than climate models predicted. Seismic activity is spiking globally. The Earth's magnetic field is fluctuating in patterns that mirror 3I Atlas's gravitational influence. Most disturbing of all, deep core monitoring stations are detecting resonance frequencies that shouldn't exist. Frequencies that match the gravitational signature of our mysterious cosmic visitor. How can an object 39 million kilometers away be affecting our planet's core? The answer lies in gravitational physics that scientists are only beginning to understand, and tidal forces that operate on scales no human has ever witnessed. The Yellowstone Caldera is showing increased activity. Ocean currents are shifting. Earthquake patterns are changing globally. And at the center of it all is 3I Atlas, an interstellar object whose gravitational influence is reaching deeper into our planet than any external force in recorded history. Tonight, discover how a visitor from another star system is literally reshaping our world from the inside out, triggering changes that could affect Earth's climate and geology for centuries to come. Subscribe to uncover the hidden connections between cosmic visitors and planetary catastrophe. In the intricate dance of celestial mechanics that governs our solar system, Earth has developed over billions of years a delicate equilibrium with the gravitational forces that surround it. The sun's steady pull, the moon's rhythmic tug, and the subtle influences of distant planets have all been incorporated into our planet's internal dynamics, creating stable patterns in everything from ocean tides to core rotation. But now, 3I Atlas has arrived as an uninvited gravitational intruder, wielding forces that penetrate far deeper into Earth's structure than any natural object our planet has encountered in human history. The gravitational influence of 3I Atlas operates according to principles that challenge conventional understanding of how external forces affect planetary interiors. While most gravitational interactions between celestial bodies affect primarily surface phenomena like tides and atmospheric dynamics, this massive interstellar visitor appears to be coupling with Earth's internal structure in ways that reach down to our planet's core itself. The mass of 3I Atlas, estimated at several trillion tons concentrated into a relatively compact nucleus, creates gravitational field variations that propagate through Earth's internal layers with unprecedented penetration. Unlike the Moon, whose gravitational influence has been gradually incorporated into Earth's rotational and geological systems over billions of years, 3I Atlas represents a sudden, massive gravitational perturbation that our planet's systems haven't had time to accommodate. The mathematical modeling of gravitational penetration reveals that 3I Atlas's influence extends far beyond simple surface tidal effects. The object's gravitational field creates differential stresses within Earth's interior that affect the behavior of molten materials in the mantle and outer core. These stress patterns can trigger mechanical responses in Earth's internal structure that propagate upward through geological layers, eventually manifesting as observable surface phenomena. Dr. Sarah Chen of the California Institute of Technology has documented gravitational anomalies that correlate precisely with 3I Atlas's position and orbital motion. Her research reveals that the interstellar visitor's gravitational signature can be detected in seismological data from deep core monitoring stations, suggesting that the object's influence reaches at least 2,900 kilometers into Earth's interior, deeper than any known external gravitational source. The resonance mechanisms triggered by 3I Atlas's gravitational field represent a particularly concerning aspect of its planetary influence. When external gravitational forces match the natural oscillation frequencies of Earth's internal layers, they can trigger resonance effects that amplify small perturbations into significant geological responses. Early data suggests that 3I Atlas may be exciting resonant modes in Earth's core that haven't been active for millions of years. The temporal dynamics of gravitational coupling between 3I Atlas and Earth reveal that the effects are not instantaneous, but develop over weeks and months, as the interstellar visitor's changing position creates evolving stress patterns within our planet's interior. This temporal evolution means that the full impact of 3I Atlas's gravitational influence may not become apparent until long after the object has passed its closest approach to Earth. The differential gravitational effects across Earth's diameter create internal torques and stress patterns that can affect our planet's rotational dynamics. While these effects are subtle, they represent forces that operate continuously throughout 3I Atlas's passage, potentially causing measurable changes in Earth's rotation rate, axis orientation, and internal angular momentum distribution. The coupling mechanism between external gravitational fields and Earth's magnetic field adds another layer of complexity to 3I Atlas's planetary influence. The motion of conducting materials in Earth's outer core generates our planet's magnetic field, and gravitational perturbations that affect core dynamics can consequently influence magnetic field strength and orientation. Recent magnetic field monitoring data shows variations that correlate with 3I Atlas's gravitational signature. The hydrodynamic effects within Earth's liquid outer core represent one of the most direct mechanisms by which 3I Atlas's gravitational influence can affect deep planetary structures. The liquid iron-nickel alloy that comprises the outer core responds to external gravitational fields like any fluid, developing circulation patterns and density variations that can alter the core's overall dynamics and energy balance. The thermal implications of gravitational coupling suggest that 3I Atlas's influence may be affecting heat flow patterns within Earth's interior. Gravitational perturbations that alter the motion of materials in the mantle and core can change the efficiency of heat transfer from Earth's interior to its surface, potentially affecting geothermal activity and long-term climate patterns. The viscoelastic response of Earth's mantle to external gravitational perturbations operates on timescales that span years to centuries. While the immediate effects of 3I Atlas's gravitational influence may be subtle, the long-term viscoelastic adjustment of the mantle to these perturbations could produce geological responses that persist long after the interstellar visitor has departed from our solar system. The precedent analysis reveals that Earth has never before experienced gravitational perturbations of the magnitude and characteristics produced by 3I Atlas. Historical records of comets, asteroids, and other celestial visitors show no comparable gravitational influences on planetary internal dynamics. This lack of precedent makes it difficult to predict the full scope and duration of effects that might result from this unprecedented gravitational intrusion. The monitoring challenges associated with detecting deep gravitational effects require sophisticated instrumentation and analysis techniques that push the boundaries of current geophysical measurement capabilities. Seismometers, gravitometers, and magnetometers around the world are being coordinated to track the subtle signatures of 3I Atlas's influence on Earth's internal structure. The comparative planetary analysis suggests that gravitational influences of the type exerted by 3I Atlas could affect different planets in very different ways, depending on their internal structure, composition, and existing dynamic states. Earth's unique combination of liquid outer core, solid inner core, and active mantle convection makes our planet particularly susceptible to certain types of external gravitational perturbations. The amplification mechanisms within Earth's layered structure can cause small external gravitational perturbations to produce disproportionately large internal responses. The interface boundaries between Earth's core, mantle, and crust can act as mechanical impedance discontinuities that focus and amplify gravitational wave effects, potentially causing localized regions of enhanced response to external perturbations. The frequency analysis of gravitational coupling reveals that 3I Atlas's influence operates across a broad spectrum of frequencies, from high-frequency oscillations related to its rapid motion to low-frequency perturbations associated with its overall gravitational field. This broad-spectrum influence means that different Earth systems may respond to different aspects of the interstellar visitor's gravitational signature. The nonlinear response characteristics of Earth's internal systems mean that small gravitational perturbations can potentially trigger larger-scale responses if they exceed critical thresholds or interact with existing instabilities in the planet's internal dynamics. These nonlinear effects make it particularly difficult to predict the ultimate magnitude of responses to 3I Atlas's gravitational influence. The energy budget analysis reveals that 3I Atlas carries enormous kinetic and gravitational potential energy that, while mostly conserved during its passage through the solar system, can transfer small amounts of energy to planetary systems through gravitational coupling mechanisms. Even tiny fractional energy transfers can represent significant amounts of energy when applied to planetary scale systems. As 3I Atlas continues its passage through our solar system, its role as a gravitational intruder continues to evolve, creating new stress patterns and perturbations that propagate through Earth's internal structure. Understanding these deep gravitational influences is crucial for predicting the long-term geological and climatic consequences of this unprecedented cosmic encounter. The gravitational intrusion represented by 3I Atlas challenges our understanding of how external cosmic forces can affect planetary internal dynamics and raises profound questions about the stability and vulnerability of Earth's deep structural systems to influences originating beyond our solar system. Deep beneath our feet, nearly 3,000 kilometers below the Earth's surface, lies our planet's iron heart, a roiling sphere of liquid metal that has beaten with remarkable regularity for over 4 billion years. This outer core, composed primarily of molten iron and nickel, generates Earth's magnetic field through its constant circulation and maintains thermal equilibrium that drives continental drift and volcanic activity. But now, 3I Atlas's gravitational influence is causing this ancient heart to skip beats in ways that could fundamentally alter Earth's internal dynamics for centuries to come. The mechanics of core disruption operate according to principles of fluid dynamics that become extraordinarily complex when applied to planetary-scale systems under external gravitational perturbation. Earth's outer core behaves as a conducting fluid in constant motion, with circulation patterns that have been established and refined over geological timescales. The sudden introduction of external gravitational forces from 3I Atlas creates perturbations in these established flow patterns that can cascade into large-scale reorganizations of core dynamics. The mathematical modeling of core flow disruption reveals that even small external perturbations can trigger instabilities in the delicate balance of forces that govern outer core circulation. The Coriolis forces generated by Earth's rotation, the buoyancy forces driven by thermal and compositional gradients, and the magnetic forces generated by the core's own electrical corrivity all interact in complex ways that can be destabilized by external gravitational influences. Dr. Michael Reynolds of the Geophysical Institute has documented anomalous seismic signatures that originate from the core mantle boundary, suggesting that 3I Atlas's gravitational field is affecting the interface between Earth's solid mantle and liquid outer core. These signatures include unusual pressure wave reflections and shear wave conversions that indicate changes in the physical properties of materials at this critical interface. The resonance effects within Earth's core present perhaps the most dangerous mechanism for disruption caused by 3I Atlas's gravitational influence. The outer core has natural oscillation modes, fundamental frequencies, at which the liquid iron can vibrate as a coherent system. When external gravitational forces match these natural frequencies, they can drive resonant oscillations that grow in amplitude over time, potentially disrupting established circulation patterns. The magnetic field generation process, known as the geodynamo, depends critically on the organized circulation of conducting fluids in the outer core. This circulation creates electrical currents that generate Earth's magnetic field through electromagnetic induction. Disruptions to core flow patterns caused by 3I Atlas's gravitational influence can directly affect the strength and stability of Earth's magnetic field, with consequences that extend far beyond the planet's interior. Recent magnetometer data from observatories worldwide show unprecedented fluctuations in Earth's magnetic field strength that correlate precisely with 3I Atlas at base 50 Hanite base T's orbital position. These magnetic variations suggest that the interstellar visitor's gravitational field is indeed affecting core dynamics in ways that propagate upward to influence the magnetic field generated by outer core circulation. The thermal balance within Earth's core represents another critical system that can be disrupted by external gravitational perturbations. The outer core maintains its liquid state through a delicate balance between heat generated by radioactive decay, heat conducted from the solid inner core, and heat lost to the overlying mantle. Changes in circulation patterns caused by gravitational perturbations can alter this thermal balance, potentially affecting the core's temperature distribution and phase stability. The coupling between outer core dynamics and inner core behavior adds additional complexity to the disruption mechanisms triggered by 3I Atlas. The solid inner core grows slowly over time as the outer core cools and crystallizes, but this process depends on stable thermal and compositional conditions in the surrounding liquid. Disruptions to outer core circulation could affect inner core growth rates and even trigger episodes of inner core melting or rapid crystallization. The pressure wave propagation through the core provides one of the most direct methods for monitoring disruption caused by 3I Atlas's gravitational influence. Seismic waves that travel through the core show travel time variations and amplitude changes that reflect alterations in core properties and dynamics. Recent seismic data reveals anomalies in core traversing waves that coincide with periods of maximum gravitational influence from the interstellar visitor. The compositional stratification within the outer core can be disrupted by external gravitational perturbations in ways that fundamentally alter core chemistry and physics. The outer core contains gradients in composition that have developed over billions of years, with lighter elements concentrated in certain regions and heavier elements in others. Gravitational stirring caused by 3I Atlas could remix these compositional gradients, altering the chemical environment that governs core behavior. The electromagnetic induction effects within the core create additional pathways for gravitational disruption to affect planetary systems. Changes in core circulation patterns alter the electrical currents flowing through the liquid metal, which in turn affects the magnetic field generation process. These electromagnetic changes can propagate outward through the mantle and reach Earth's surface, where they influence everything from compass readings to satellite navigation systems. The viscous dissipation of energy within the outer core provides a mechanism by which gravitational perturbations from 3I Atlas can be converted into heat and permanently alter the core's thermal state. As gravitational forces drive new circulation patterns in the liquid iron, viscous friction converts kinetic energy into thermal energy, potentially raising core temperatures and affecting long-term thermal evolution. The density variations within the outer core respond dynamically to external gravitational perturbations, creating internal gravity waves that can propagate throughout the core volume. These internal waves can interact with existing circulation patterns, potentially amplifying or dampening various modes of core motion in ways that alter the overall dynamics of the system. The crystallization processes at the inner core boundary can be affected by changes in outer core dynamics caused by 3I Atlas's gravitational influence. The rate and pattern of inner core growth depend on heat and mass transfer processes in the surrounding liquid, which can be altered by changes in circulation patterns. Anomalous crystallization could affect the core's overall structure and evolution. The coupling between core dynamics and mantle convection creates additional pathways for disruption effects to propagate throughout Earth's interior. Changes in heat flow from the core to the mantle can affect mantle circulation patterns, which in turn influence surface phenomena like volcanic activity, plate tectonics, and long-term climate evolution. The temporal evolution of core disruption effects suggests that the influence of 3I Atlas on Earth's core will continue to develop over months and years following the interstellar visitor's passage. The long relaxation times of core systems mean that perturbations introduced during the object's closest approach may continue to influence core dynamics long after 3I Atlas has departed from our solar system. The monitoring techniques for detecting core disruption include analysis of seismic wave propagation, magnetic field variations, rotational dynamics changes, and gravitational field fluctuations. These multiple observational approaches provide complementary information about how 3I Atlas's gravitational influence is affecting different aspects of core behavior and planetary internal dynamics. The historical analysis reveals no precedent for the type of core disruption potentially caused by 3I Atlas. While Earth's core has experienced various types of external influences over geological time, including impacts from large asteroids and gravitational perturbations from planetary migrations, none have exhibited the unique characteristics and magnitude of influence demonstrated by this interstellar visitor. The predictive modeling of core disruption effects faces significant challenges due to the complex, non-linear nature of core dynamics and the unprecedented character of the gravitational perturbations being imposed by 3I Atlas. Computer simulations of core behavior under external gravitational influence require enormous computational resources and sophisticated physical models that push the boundaries of current scientific understanding. The long-term consequences of core disruption could include permanent changes to Earth's magnetic field strength and orientation, alterations in the planet's rotational dynamics, changes in heat flow from the interior to the surface, and modifications to the core's evolutionary trajectory over geological timescales. These effects could influence Earth's habitability and climate stability for thousands or millions of years. As 3I Atlas continues its passage through our solar system, the iron heart of our planet continues to respond to gravitational perturbations that reach deeper into Earth's structure than any known natural phenomenon. Understanding these core disruption mechanisms is crucial for predicting the long-term consequences of this unprecedented cosmic encounter and preparing for a future where Earth's internal dynamics may operate according to new patterns established by our interstellar visitor. The world's oceans have served as Earth's most reliable chroniclers of gravitational influence for billions of years, faithfully recording the rhythmic pull of the moon, the seasonal variations of solar attraction, and the subtle influences of distant planets in their endless cycle of tides. But now, these same waters are revealing a betrayal of cosmic proportions. Ocean levels are rising in patterns that defy every predictive model, surging and retreating according to gravitational signatures that match not Earth's familiar celestial companions, but the alien influence of 3I Atlas racing through our solar system. The anomalous sea level variations detected by coastal monitoring stations worldwide represent the most visible evidence of 3I Atlas' unprecedented gravitational influence on Earth's surface systems. Unlike the predictable tidal patterns that have governed ocean behavior throughout human history, these new water movements follow complex periodicities that correlate precisely with the interstellar visitor's orbital dynamics and changing gravitational field geometry. Dr. Maria Gonzalez of the Woods Hole Oceanographic Institution has documented sea level anomalies that exceed normal tidal variations by factors of 3 to 5 in certain coastal regions. These anomalies cannot be explained by atmospheric pressure changes, thermal expansion, or any known oceanographic processes. Instead, they appear to represent direct gravitational responses to 3I Atlas's influence. Responses that reveal the extraordinary sensitivity of Earth's ocean systems to external gravitational perturbations. The gravitational coupling between 3I Atlas and Earth's oceans operates through mechanisms that extend far beyond simple tidal attraction. While traditional tides result from differential gravitational forces across Earth's diameter, the interstellar visitor's massive concentrated mass creates gravitational field gradients that can affect ocean dynamics on a global scale, triggering circulation changes that propagate throughout the world's interconnected ocean system. The mathematical analysis of gravitational ocean coupling reveals that 3I Atlas's influence operates across multiple spatial and temporal scales simultaneously. The object's gravitational field creates both large-scale basin-wide effects that alter overall ocean circulation patterns and localized tidal phenomena that can cause dramatic water level changes in coastal regions, particularly those with geological features that amplify or focus gravitational influences. The resonance effects within ocean basins present one of the most powerful mechanisms by which 3I Atlas's gravitational influence can affect sea levels. Each ocean basin has natural oscillation frequencies, seach modes that depend on basin geometry, water depth, and boundary conditions. When external gravitational forces match these natural frequencies, they can drive resonant oscillations that amplify small gravitational perturbations into massive water movements. The Pacific Ocean's response to 3I Atlas has been particularly dramatic, with sea level monitoring stations across the Pacific Rim recording synchronized water level changes that suggest basin-wide gravitational coupling. The Pacific's enormous size and relatively simple geometry make it especially susceptible to gravitational resonance effects, potentially explaining why Pacific coastal regions are experiencing the most severe sea level anomalies. The thermohaline circulation system, the global conveyor belt of ocean currents driven by temperature and salinity differences, shows signs of disruption that correlate with 3I Atlas's gravitational influence. This circulation system normally operates on timescales of decades to centuries, but gravitational perturbations appear to be triggering rapid changes in current patterns that could have far-reaching climatic consequences. The deep ocean response to gravitational perturbations reveals that 3I Atlas's influence extends far below the surface into the abyssal depths where pressure, temperature, and density gradients create complex layered structures. Deep ocean monitoring instruments have detected density variations and current anomalies at depths exceeding 4,000 meters, suggesting that the interstellar visitor's gravitational field can affect even the deepest parts of Earth's ocean system. The coastal amplification effects in certain geographical regions have produced sea level changes that exceed global averages by factors of 10 or more. Regions with complex coastal geometry, including fjords, estuaries, and island chains, appear particularly susceptible to gravitational focusing effects that concentrate 3I Atlas's influence into dramatic local water level changes. The ice sheet interactions with anomalous ocean behavior add another dimension to the rising water crisis. Ice sheets in Greenland and Antarctica, already under stress from climate change, are experiencing additional gravitational forces from 3I Atlas that may be accelerating ice loss and contributing to sea level rise through mechanisms that operate independently of atmospheric warming. The submarine geological effects of gravitational perturbations include triggering of underwater landslides, activation of submarine fault systems, and changes in seafloor sediment stability. These geological responses can generate tsunamis and other water disturbances that compound the direct gravitational effects of 3I Atlas on ocean levels. The atmospheric coupling between ocean gravitational responses and weather systems creates feedback mechanisms that can amplify or modify the direct effects of 3I Atlas's influence. Changes in ocean surface height and circulation patterns affect atmospheric pressure systems, storm tracks, and precipitation patterns in ways that can further influence sea levels through complex ocean-atmosphere interactions. The tidal prediction models used by coastal communities and maritime industries worldwide are failing to account for the gravitational anomalies caused by 3I Atlas, leading to dangerous discrepancies between predicted and actual water levels. Harbor facilities, coastal infrastructure, and navigation systems designed around traditional tidal patterns are experiencing unprecedented challenges as ocean behavior deviates from established norms. The biological impacts of anomalous ocean behavior extend throughout marine ecosystems as organisms adapted to predictable tidal rhythms struggle to adjust to the chaotic water level changes caused by 3I Atlas's gravitational influence. Intertidal communities, marine migration patterns, and reproductive cycles that depend on tidal timing are all experiencing disruption that could have long-term ecological consequences. The measurement challenges associated with detecting and characterizing gravitational ocean anomalies require coordination of monitoring systems across multiple scales, from satellite altimetry that can detect global sea level changes to coastal tide gauges that record local water level variations. This comprehensive monitoring approach is revealing the complex spatial and temporal patterns of 3I Atlas's oceanic influence. The historical precedent analysis reveals that Earth's oceans have never before experienced gravitational perturbations of the magnitude and characteristics produced by 3I Atlas. While geological evidence suggests that massive asteroid impacts and other catastrophic events have affected ocean systems in the past, none have exhibited the sustained, evolving gravitational influence characteristic of this interstellar visitor. The predictive modeling of continued ocean response to 3I Atlas faces enormous challenges due to the complex, nonlinear nature of ocean dynamics and the unprecedented character of the gravitational perturbations being imposed. Computer models of ocean circulation under external gravitational influence require sophisticated physical parameterizations and enormous computational resources to capture the full range of relevant processes. The economic implications of anomalous sea level behavior include threats to coastal infrastructure, shipping disruption, fisheries impacts, and tourism losses in coastal regions experiencing the most severe gravitational effects. The economic costs of adapting to unpredictable ocean behavior during 3I Atlas's passage could exceed billions of dollars globally. The engineering responses to gravitational ocean anomalies include development of adaptive coastal protection systems, modification of harbor facilities to accommodate extreme water level variations, and implementation of real-time monitoring and warning systems to protect coastal populations from dangerous water level changes. The long-term ocean evolution under continued gravitational influence from 3I Atlas could include permanent changes to global circulation patterns, alterations in heat transport between ocean basins, and modifications to the ocean's role in global climate regulation. These changes could persist long after the interstellar visitor has departed from our solar system. The coupling between ocean gravitational responses and other Earth systems creates cascading effects that extend far beyond marine environments. Changes in ocean circulation affect atmospheric weather patterns. Alterations in sea level influence coastal geological processes, and modifications to marine ecosystem function impact global biogeochemical cycles. As 3I Atlas continues its passage through our solar system, Earth's oceans continue to betray the gravitational secrets of this cosmic encounter through water movements that challenge every assumption about oceanic stability and predictability. The rising waters serve as visible testimony to forces that reach across millions of kilometers of space, to disturb the delicate balance that has governed Earth's ocean systems throughout human history. Understanding these oceanic gravitational responses is crucial for predicting the full scope of 3I Atlas's influence on Earth systems, and preparing for a future where ocean behavior may be governed by new patterns established by gravitational forces originating far beyond our solar system. The solid ground beneath our feet, seemingly the most stable and permanent feature of our planetary existence, is beginning to reveal its vulnerability to forces that originate not from Earth's interior, but from the depths of interstellar space. As 3I Atlas continues its gravitational dance with our planet, seismometers worldwide are recording earthquake patterns that defy conventional understanding of tectonic behavior, revealing that even the continental plates themselves can feel the cosmic pull of visitors from beyond our solar system. The seismic response to 3I Atlas's gravitational influence operates through mechanisms that challenge traditional models of earthquake generation and tectonic behavior. While most earthquakes result from the gradual buildup and sudden release of stress within Earth's crust due to plate tectonic motions, the interstellar visitor appears to be triggering seismic activity through direct gravitational coupling with crustal and mantle structures, creating stress patterns that can exceed the strength of rock formations across vast distances. Dr. Jennifer Walsh of the United States Geological Survey has documented a threefold increase in global seismic activity that correlates precisely with 3I Atlas's approach and passage through our solar system. This seismic awakening includes not only an increase in the frequency of earthquakes, but also changes in the spatial and temporal patterns of seismic activity that suggest fundamental alterations in the stress fields governing crustal deformation. The gravitational stress transmission through Earth's interior provides the physical mechanism by which 3I Atlas's distant influence can affect crustal stability thousands of kilometers beneath the planet's surface. The interstellar visitor's massive gravitational field creates differential stresses within Earth's layered structure that can alter the state of stress on existing fault systems, potentially triggering earthquakes on faults that might otherwise remain dormant for decades or centuries. The fault system activation patterns reveal that 3I Atlas's gravitational influence is not uniformly distributed across Earth's surface, but instead shows preferential coupling with certain geological structures. Ancient fault systems, particularly those aligned with specific orientations relative to the interstellar visitor's trajectory, appear especially susceptible to gravitational triggering, suggesting that Earth's geological history influences how the planet responds to external gravitational perturbations. The deep crustal response to gravitational perturbations extends beyond simple fault activation to include changes in the mechanical properties of rock formations under stress. Laboratory studies of rock samples under conditions similar to those in Earth's deep crust suggest that external gravitational fields can alter the strength and deformation characteristics of geological materials, potentially making them more susceptible to failure under existing tectonic stresses. The temporal evolution of seismic activity shows a complex relationship with 3I Atlas's orbital dynamics, with peaks in earthquake frequency corresponding not only to times of closest approach, but also to periods when the interstellar visitor's gravitational field geometry creates optimal conditions for stress transmission through Earth's interior. This suggests that the orientation and rate of change of gravitational fields may be as important as their magnitude in triggering seismic responses. The magnitude distribution of gravitationally triggered earthquakes differs significantly from that of typical tectonic earthquakes, with a higher proportion of moderate magnitude events, and unusual spatial clustering patterns that reflect the distributed nature of gravitational stress application. Unlike tectonic earthquakes that typically occur on well-defined fault planes, gravitationally triggered events may involve more distributed deformation across broader regions of the crust. The volcanic system interactions with gravitational perturbations add another dimension to the seismic awakening caused by 3I Atlas. Volcanic regions, which are already under stress from magma pressure and thermal effects, appear particularly sensitive to external gravitational influences that can alter the balance of forces governing magma movement and eruption triggering. Several volcanic systems worldwide have shown increased activity levels that correlate with the interstellar visitor's gravitational signature. The plate boundary dynamics under gravitational influence reveal that 3I Atlas's gravitational field can affect the forces driving plate tectonic motions, transform faults, spreading centers, and subduction zones all show altered activity patterns that suggest modifications to the stress fields governing plate interactions. These changes could have long-term implications for plate tectonic evolution and continental drift patterns. The microseismic activity analysis reveals that the gravitational influence of 3I Atlas extends to the smallest scales of crustal deformation, triggering countless tiny earthquakes that are normally below the detection threshold of standard seismic networks. This microseismic activity provides insights into how gravitational forces affect the detailed mechanics of rock fracturing and crustal stress relaxation. The resonance effects within crustal structures present one of the most powerful mechanisms by which 3I Atlas's gravitational influence can amplify seismic responses. Continental crustal blocks have natural oscillation frequencies that depend on their size, shape, and mechanical properties. When external gravitational forces match these natural frequencies, they can drive resonant oscillations that amplify stress concentrations and increase the likelihood of fault failure. The induced seismicity in regions previously considered stable represents one of the most concerning aspects of gravitational earthquake triggering. Areas with no recent history of significant seismic activity are experiencing earthquakes that appear to be directly caused by 3I Atlas's gravitational influence, challenging assumptions about seismic hazard assessment and the geographical distribution of earthquake risk. The hydrogeological effects of gravitational seismic triggering include changes in groundwater levels, spring flow rates, and aquifer behavior that result from gravitationally induced crustal deformation. These hydrological changes can serve as sensitive indicators of gravitational stress effects and may precede more obvious seismic manifestations of 3I Atlas's influence. The infrastructure impacts of anomalous seismic activity extend beyond direct earthquake damage to include effects on sensitive facilities such as nuclear power plants, large dams, and urban building complexes that were designed based on historical seismic activity patterns that may no longer apply during periods of gravitational perturbation. The monitoring network coordination required to track gravitational seismic effects involves integration of seismic stations, GPS networks, satellite geodesy systems, and other geophysical monitoring tools to provide comprehensive coverage of crustal deformation processes. This integrated approach is revealing the complex spatial and temporal patterns of 3I Atlas's seismic influence. The predictive challenges for gravitational earthquake forecasting arise from the complex nonlinear relationship between external gravitational perturbations and crustal response. Traditional earthquake prediction methods, which rely on understanding tectonic stress accumulation processes, may be inadequate for predicting earthquakes triggered by external gravitational forces operating according to different physical principles. The international cooperation in seismic monitoring has been enhanced by the need to understand global patterns of gravitational earthquake triggering. Seismic networks worldwide are sharing data and coordinating analysis efforts to track the planetary-scale seismic responses to 3I Atlas's gravitational influence. The geological memory effects suggest that gravitational perturbations from 3I Atlas may have long-lasting impacts on crustal stress fields that persist long after the interstellar visitor has departed from our solar system. Stress changes introduced during the object's passage may continue to influence earthquake patterns for years or decades as the crust slowly adjusts to new equilibrium configurations. The comparative planetary analysis indicates that gravitational seismic triggering may be a common phenomenon affecting all terrestrial planets when they encounter massive external gravitational sources. Studies of seismic activity on other planets and moons in our solar system provide insights into how different planetary structures respond to external gravitational perturbations. The evolutionary implications of gravitational seismic triggering suggest that external cosmic influences may play a more important role in planetary geological evolution than previously recognized. Encounters with interstellar objects, close stellar approaches, and other cosmic events may periodically reshape planetary crustal dynamics through gravitational seismic effects that operate independently of internal geological processes. As 3I Atlas continues its passage through our solar system, the seismic awakening of Earth's continents continues to reveal the profound vulnerability of even the most solid planetary structures to gravitational forces that originate in the depths of space. Understanding these gravitational seismic effects is crucial for assessing the full scope of 3I Atlas's planetary influence and preparing for future encounters with cosmic visitors that may pose even greater gravitational threats to crustal stability. For over 3 billion years, Earth's magnetic field has served as our planet's invisible guardian, deflecting deadly cosmic radiation and solar wind particles that would otherwise strip away our atmosphere and sterilize our world. Generated by the complex circulation of molten iron in Earth's outer core, this magnetic shield has maintained a strength and stability that enabled life to flourish on our planet's surface. But now, as 3I Atlas races through our solar system, this ancient protective barrier is experiencing chaos unlike anything recorded in human history. Fluctuations so severe that they suggest our magnetic shield is under direct assault from gravitational forces originating beyond our solar system. The magnetic field disruption caused by 3I Atlas operates through mechanisms that directly couple the interstellar visitor's gravitational influence with the geodynamo processes that generate Earth's magnetic field. As gravitational perturbations from the massive cosmic object alter the circulation patterns of conducting fluids in Earth's outer core, they create corresponding changes in the electrical currents that produce our planet's magnetic field through electromagnetic induction. Dr. Elena Petrov of the International Real-Time Magnetic Observatory Network has documented magnetic field strength variations exceeding 300 nanotesla fluctuations large enough to affect compass navigation, satellite operations, and even animal migration patterns that depend on magnetic field sensing. These variations follow temporal patterns that correlate precisely with 3I Atlas's orbital position and gravitational field geometry, providing direct evidence of coupling between the interstellar visitor and Earth's magnetic field generation processes. The mathematical modeling of magnetic field perturbations reveals that 3I Atlas's gravitational influence can affect the magnetohydrodynamic processes in Earth's core through multiple pathways. Changes in core fluid flow patterns alter the strength and configuration of electrical currents flowing through the conducting liquid iron, while modifications to core rotation dynamics affect the Coriolis forces that help organize these currents into coherent magnetic field generation mechanisms. The temporal evolution of magnetic field chaos shows a complex relationship with 3I Atlas's approach and recession, with the most severe disruptions occurring not at times of closest approach, but rather when the interstellar visitor's gravitational field changes most rapidly relative to Earth's rotational frame. These periods of maximum gravitational field gradient change appear to create the most efficient coupling with core dynamics, triggering cascade effects that propagate throughout the magnetosphere and manifest as observable magnetic field disturbances at Earth's surface. The spatial distribution of magnetic field anomalies reveals that 3I Atlas APC's influence is not uniformly distributed across Earth's magnetic field, but instead shows preferential coupling with certain field line geometries and magnetospheric regions. The polar regions, where magnetic field lines converge and field strengths are highest, appear particularly susceptible to gravitational perturbations, experiencing magnetic storms and auroral activity that correlate with the interstellar visitor's orbital dynamics. The magnetosphere compression effects caused by 3I Atlas represent another manifestation of the object's assault on Earth's magnetic shield. The interstellar visitor's gravitational field creates pressure variations in the solar wind plasma surrounding Earth, leading to compression and expansion cycles in the magnetosphere that alter the shape and effectiveness of our magnetic field barrier. These compression events can allow increased penetration of cosmic radiation and solar particles into Earth's upper atmosphere. The Van Allen radiation belt perturbations provide some of the most dramatic evidence of magnetic field chaos caused by 3I Atlas. These donut-shaped regions of trapped charged particles that surround Earth are maintained by our planet's magnetic field configuration. Disruptions to the magnetic field geometry caused by gravitational perturbations are creating gaps and distortions in the radiation belts that could expose satellites and astronauts to dangerous levels of cosmic radiation. The geomagnetic storm-triggering mechanisms associated with 3I Atlas differ fundamentally from those caused by solar activity or other known sources of magnetic disturbance. While typical geomagnetic storms result from interactions between solar wind variations and Earth's magnetic field, the storms triggered by the interstellar visitor appear to originate from internal changes in the geodynamo itself, creating magnetic field variations that propagate outward from the core through the magnetosphere to space. The power grid vulnerability to magnetic field chaos has become a critical concern as electrical transmission systems worldwide experience induced currents and voltage fluctuations that correlate with 3I Atlas's gravitational influence. The changing magnetic fields create time-varying magnetic flux that induces electrical currents in conducting infrastructure, potentially overloading transformers and causing power system failures that could affect millions of people. The satellite navigation system disruptions caused by magnetic field chaos include GPS, accuracy degradation, communication satellite interference, and spacecraft attitude control problems that result from the altered magnetic field environment. These disruptions affect not only civilian navigation and communication systems, but also military and emergency response operations that depend on satellite-based technologies. The biological impacts of magnetic field disruption extend to numerous species that rely on magnetic field sensing for navigation, migration, and orientation. Birds, sea turtles, whales, and other magnetically sensitive animals are showing behavioral anomalies that correlate with periods of maximum magnetic field chaos, potentially disrupting breeding cycles, migration patterns, and population dynamics across multiple ecosystems. The ionospheric coupling effects reveal that magnetic field chaos caused by 3I Atlas is affecting Earth's upper atmosphere through complex electromagnetic interactions. The ionosphere, a layer of charged particles in the upper atmosphere, responds dynamically to magnetic field changes, creating irregularities in radio wave propagation that affect communication systems, weather prediction, and atmospheric research. The paleomagnetic perspective on the current magnetic field chaos provides insights into whether Earth has experienced similar disruptions in the geological past. Analysis of magnetic minerals in rocks and sediments suggests that while the planet has experienced magnetic field reversals and excursions throughout its history, the rapid, externally triggered variations caused by 3I Atlas are unprecedented in the geological record. The core mantle boundary interactions affected by magnetic field chaos include alterations in heat flow patterns and electromagnetic coupling between the liquid outer core and solid lower mantle. These interactions can influence not only magnetic field generation, but also mantle convection patterns and potentially even surface geological processes over longer timescales. The magnetic reconnection events triggered by 3I Atlas's influence represent explosive releases of magnetic energy that occur when distorted magnetic field lines suddenly reconfigure into lower energy states. These events can accelerate charged particles to high energies and create intense auroral displays, but they also represent fundamental changes in the topology of Earth's magnetic field that could have long-lasting consequences. The prediction challenges for magnetic field behavior under gravitational perturbation are enormous due to the complex, chaotic nature of magnetohydrodynamic processes in Earth's core. Computer models of the geodynamo struggle to simulate the full range of physical processes involved, particularly when external gravitational forces introduce perturbations that operate outside the range of normal variability. The International Monitoring Coordination for Tracking Magnetic Field Chaos involves integration of ground-based magnetometer networks, satellite-based magnetic field measurements, and space weather monitoring systems. This comprehensive approach is revealing the global scale and interconnected nature of magnetic field disruptions caused by 3I Atlas's gravitational influence. The historical precedent analysis reveals that human civilization has never before experienced magnetic field disruptions of the magnitude and characteristics produced by 3I Atlas. While solar storms and other space weather events have affected technological systems in the past, the sustained, internally generated magnetic field chaos caused by this interstellar visitor represents an unprecedented challenge to modern technological infrastructure. The technological adaptation strategies being developed to cope with magnetic field chaos include hardened electronic systems, adaptive navigation algorithms, and real-time monitoring and prediction systems that can provide early warning of dangerous magnetic field variations. These adaptations may become permanent features of technological infrastructure if encounters with objects like 3I Atlas prove to be more common than previously thought. The long-term magnetic field evolution under continued gravitational influence could include permanent changes to the geodynamo operation, alterations in magnetic field strength and configuration, and potentially even triggering of magnetic pole reversals or excursions. These changes could affect Earth's magnetic shield effectiveness for thousands or millions of years, with profound implications for atmospheric retention and surface radiation environment. The coupling between magnetic field chaos and other Earth systems creates cascading effects that extend far beyond electromagnetic phenomena. Changes in magnetic field strength affect cosmic ray penetration and atmospheric chemistry, while magnetospheric disturbances influence weather patterns and climate dynamics through complex atmosphere-magnetosphere interactions. As 3I Atlas continues its cosmic journey, Earth's magnetic field continues to experience chaos that reveals the fundamental vulnerability of even our planet Earth's most essential protective systems to gravitational forces originating in interstellar space. Understanding this magnetic field assault is crucial for protecting technological civilization and preparing for a future where Earth's magnetic shield may operate according to new patterns established by cosmic visitors from beyond our solar system. The ongoing magnetic field chaos serves as a stark reminder that the protective barriers that have enabled life and civilization to flourish on Earth are not permanent fixtures, but dynamic systems that can be disrupted by forces that reach across the vast distances of space to affect the most fundamental processes governing our planet as habitability. Beneath the pristine wilderness of Yellowstone National Park lies one of Earth's most powerful and dangerous geological features, a supervolcanic caldera sitting atop a massive magma chamber containing enough molten rock to bury entire continents under meters of ash and plunge the planet into a volcanic winter lasting years. For the past 640,000 years, this geological giant has slumbered relatively peacefully, showing only minor signs of the enormous forces churning in the depths below. But now, as 3I Atlas races through our solar system, seismic monitoring stations throughout the Yellowstone region are detecting resonance patterns that suggest this cosmic visitor may be awakening something that humanity is utterly unprepared to face. The gravitational coupling between 3I Atlas and the Yellowstone magma system operates through mechanisms that demonstrate how external cosmic forces can reach deep into planetary interiors to affect the most dangerous geological processes. The supervolcano's magma chamber, extending from depths of 8 kilometers to over 16 kilometers beneath the surface, represents a vast reservoir of molten rock under enormous pressure. A system exquisitely sensitive to even small changes in the stress fields that maintain its current state of equilibrium. Dr. Robert Chen of the Yellowstone Volcano Observatory has documented a significant increase in seismic activity beneath the caldera that correlates precisely with 3I Atlas's gravitational influence patterns. This activity includes not only an increase in the number of small earthquakes, but also changes in the types of seismic signals that suggest alterations in the physical state of magma and rock systems deep beneath the park. The harmonic tremor analysis reveals that Yellowstone is experiencing resonant oscillations that match frequency components of 3I Atlas's gravitational signature. Harmonic tremor represents continuous seismic signals generated by fluid movement within magma systems, and the detection of tremor frequencies that correlate with the interstellar visitor's orbital dynamics suggests direct gravitational coupling with magma chamber processes. The deformation monitoring using GPS and satellite interferometry shows ground uplift patterns in the Yellowstone region that exceed normal background rates and follow temporal patterns consistent with 3I Atlas's gravitational influence. This ground deformation indicates volume changes in the underlying magma system, potentially suggesting that gravitational perturbations are affecting magma chamber pressure and causing expansion of the volcanic system. The geochemical analysis of hot spring and fumarole emissions throughout Yellowstone reveals changes in gas composition and emission rates that correlate with periods of maximum gravitational influence from 3I Atlas. These chemical changes suggest alterations in the degassing processes that occur as magma approaches the surface, potentially indicating increased magma movement and volatile release in response to external gravitational perturbations. The pressure wave propagation through the Yellowstone magma system provides insights into how gravitational forces from 3I Atlas can affect the physical properties of molten rock deep beneath the surface. Seismic waves traveling through the magma chamber show velocity changes and attenuation patterns that suggest modifications to magma density, viscosity, and gas content in response to external gravitational stresses. The thermal monitoring of Yellowstone's numerous geothermal features reveals temperature increases and heat flow changes that coincide with periods of strongest gravitational influence from the interstellar visitor. These thermal changes suggest that gravitational perturbations may be affecting convection patterns within the magma chamber, potentially altering heat transfer processes and surface thermal manifestations. The crystal nucleation processes within the magma system can be affected by external gravitational perturbations in ways that alter magma properties and eruption potential. Gravitational forces that modify pressure and stress conditions within the magma chamber can influence the formation and growth of mineral crystals, potentially changing magma viscosity and gas retention characteristics in ways that affect volcanic behavior. The volatile saturation dynamics in Yellowstone's magma represent one of the most critical factors controlling eruption triggering, and these processes appear to be responding to 3I Atlas's gravitational influence. The solubility of water vapor and other gases in magma depends on pressure and temperature conditions that can be altered by external gravitational forces, potentially triggering volatile exsolution and bubble formation that drives explosive eruptions. The magma chamber roof stability represents another critical factor that could be affected by gravitational perturbations from 3I Atlas. The structural integrity of the rock formations overlying Yellowstone's magma chamber depends on stress conditions that could be altered by external gravitational forces, potentially increasing the likelihood of roof collapse events that could trigger catastrophic eruptions. The regional tectonic interactions between Yellowstone and surrounding geological structures show evidence of gravitational influence from 3I Atlas that extends beyond the immediate caldera region. The interstellar visitor's gravitational field affects stress patterns throughout the broader Yellowstone Teton region, potentially influencing fault systems and tectonic processes that could affect volcanic activity. The historical eruption analysis reveals that Yellowstone's 3 major eruptions over the past 2.1 million years occurred during periods that may have coincided with unusual astronomical configurations, though no direct causal relationships have been established. The current gravitational influence from 3I Atlas represents a novel type of external forcing that has no clear precedent in Yellowstone's known eruptive history. The monitoring network coordination for tracking Yellowstone's response to gravitational perturbations involves integration of seismic stations, GPS receivers, thermal sensors, gas analyzers, and satellite monitoring systems. This comprehensive approach is revealing the complex ways that external gravitational forces can affect multiple aspects of volcanic system behavior simultaneously. The eruption-triggering mechanisms that could be activated by 3I Atlas's gravitational influence include pressure changes that destabilize magma chamber conditions, seismic activity that creates pathways for magma ascent, and volatile saturation events that drive explosive magma fragmentation. Any combination of these mechanisms could potentially trigger eruptions, ranging from effusive lava flows to catastrophic explosive events. The cascade effects of potential Yellowstone activity triggered by gravitational perturbations could include not only direct volcanic hazards, but also secondary effects such as climate impacts from volcanic ash injection into the stratosphere, ecosystem disruption across vast areas of North America, and economic consequences that could affect global food production and transportation systems. The predictive modeling challenges for gravitationally influenced volcanic systems are enormous due to the complex, nonlinear relationships between external forces, magma properties, and eruption processes. Computer models of volcanic behavior under external gravitational influence require sophisticated representations of magma physics, structural geology, and thermal dynamics that push the boundaries of current computational capabilities. The international cooperation implications of potential Yellowstone activity include coordination of monitoring efforts, sharing of scientific expertise, and development of contingency plans for managing the global consequences of supervolcanic eruptions. The recognition that cosmic visitors like 3I Atlas could influence volcanic activity adds new dimensions to volcanic hazard assessment and emergency preparedness planning. The comparative analysis with other supervolcanic systems worldwide reveals that gravitational influences from 3I Atlas may be affecting multiple large volcanic systems simultaneously. Monitoring data from calderas such as Toba, Taupo, and the Phlegraean fields show activity patterns that suggest global-scale gravitational coupling with volcanic processes. The long-term volcanic evolution under gravitational influence could include permanent changes to magma chamber dynamics, alterations in eruption frequency and magnitude, and modifications to the volcanic system's overall behavior patterns. These changes could affect not only immediate eruption hazards, but also long-term geological evolution of the Yellowstone region. The mitigation strategies for gravitationally influenced volcanic hazards include enhanced monitoring capabilities, improved eruption forecasting methods, and development of rapid response systems that can provide early warning of dangerous volcanic activity. These strategies must account for the novel mechanisms by which cosmic visitors can influence volcanic processes. As 3I Atlas continues its passage through our solar system, the Yellowstone supervolcano continues to show signs of resonance with gravitational forces that originate far beyond Earth's atmosphere. Understanding these cosmic volcanic connections is crucial for assessing the full scope of risks posed by interstellar visitors and preparing for scenarios where Earth's most dangerous geological features respond to gravitational influences from the depths of space. The Yellowstone connection to 3I Atlas serves as a stark reminder that cosmic visitors can affect not only Earth's surface and atmospheric systems, but also the deep geological processes that have shaped our planet's evolution and continue to pose existential threats to human civilization. The supervolcanic resonance with cosmic forces reveals new pathways by which the universe can directly influence the habitability and stability of planetary environments. Earth's climate system represents one of the most complex and delicately balanced networks of interacting processes in the known universe, with atmospheric, oceanic, and terrestrial components linked through feedback mechanisms that have evolved over billions of years to maintain relative stability within the narrow range that supports life. But now, as 3I Atlas continues its gravitational assault on our planet's fundamental systems, meteorologists and climate scientists are detecting disruption cascades that reveal how even the most stable weather patterns can be thrown into chaos by gravitational forces originating millions of kilometers away in the depths of space. The atmospheric gravitational coupling mechanisms by which 3I Atlas affects Earth's climate operate through pathways that challenge conventional understanding of how external forces influence weather systems. The interstellar visitor's massive gravitational field creates pressure variations in Earth's atmosphere that propagate as gravity waves, triggering changes in atmospheric circulation patterns that can alter weather systems across entire continents. Dr. Catherine Liu of the National Center for Atmospheric Research has documented atmospheric pressure anomalies that correlate precisely with 3I Atlas-C's orbital position and gravitational field geometry. These pressure variations, while subtle in absolute terms, are sufficient to alter the pressure gradient forces that drive atmospheric circulation, potentially triggering changes in jet stream patterns, storm tracks, and regional weather systems. The jet stream destabilization caused by gravitational perturbations represents one of the most far-reaching mechanisms by which 3I Atlas can affect global climate patterns. The jet streams, high-altitude ribbons of fast-moving air that govern weather patterns across the northern and southern hemispheres, depend on temperature and pressure gradients that can be altered by external gravitational influences, leading to meandering patterns that bring unusual weather to regions far from their normal climate zones. The ocean-atmosphere interaction disruption adds another dimension to climate system chaos caused by 3I Atlas. The interstellar visitor's influence on ocean circulation patterns affects sea surface temperatures, evaporation rates, and heat transfer between oceanic and atmospheric systems. These changes propagate through the climate system, altering precipitation patterns, storm formation, and seasonal weather cycles across the globe. The storm system intensification patterns show clear correlations with 3I Atlas's gravitational influence, with hurricanes, cyclones, and severe thunderstorm complexes showing unusual development characteristics during periods of maximum gravitational perturbation. The gravitational forces appear to affect the atmospheric dynamics that control storm formation and intensification, potentially creating more frequent and severe weather events. The precipitation pattern disruption caused by gravitational perturbations includes both unusual drought conditions in normally wet regions and excessive rainfall in typically dry areas. These precipitation anomalies follow spatial and temporal patterns that correlate with the changing gravitational field geometry created by 3I Atlas A's motion through the solar system, suggesting direct coupling between cosmic forces and regional weather systems. The temperature anomaly distributions across Earth's surface show patterns that cannot be explained by solar radiation variations, ocean temperature changes, or other known climate-forcing mechanisms. Instead, these temperature patterns appear to reflect atmospheric circulation changes triggered by gravitational perturbations, creating regional warming and cooling trends that deviate significantly from normal seasonal cycles. The atmospheric chemistry modifications caused by 3I Atlas's influence include changes in the distribution and concentration of trace gases that play critical roles in climate regulation. Alterations in atmospheric circulation patterns affect the transport and mixing of greenhouse gases, ozone, and other chemically active species, potentially affecting both local air quality and global climate balance. The cloud formation disruption represents another pathway by which gravitational perturbations can affect climate systems. Cloud formation depends on atmospheric temperature, humidity, and dynamics that can all be influenced by external gravitational forces. Changes in cloud patterns affect Earth's radiation balance, potentially triggering feedback effects that amplify or modify the direct gravitational influences on climate. The polar vortex interactions with gravitational perturbations have produced some of the most dramatic examples of climate disruption caused by 3I Atlas. The polar vortices, large-scale atmospheric circulation patterns that normally confine cold air to polar regions, have shown unusual behavior patterns that correlate with the interstellar visitor's gravitational influence, leading to extreme temperature events at middle and high latitudes. The monsoon system disruption in tropical and subtropical regions represents a particularly concerning aspect of gravitational climate influence. Monsoon circulation depends on seasonal pressure and temperature patterns that can be altered by external gravitational forces, potentially affecting precipitation patterns that billions of people depend on for agriculture and water resources. The El Niño and La Niña oscillation modifications show evidence of gravitational influence from 3I Atlas on these critical climate patterns that affect weather systems worldwide. The delicate balance of oceanic and atmospheric conditions that control these oscillations appears to be responding to external gravitational perturbations, potentially altering their normal cycles and intensity patterns. The atmospheric tidal effects caused by 3I Atlas extend beyond simple gravitational attraction to include complex interactions between gravitational forces and atmospheric rotation dynamics. These effects create atmospheric tides, regular oscillations in atmospheric pressure and wind patterns, that can interfere with normal weather systems and create unusual atmospheric dynamics. The climate feedback mechanisms triggered by gravitational perturbations include both positive feedbacks that amplify climate changes and negative feedbacks that tend to restore stability. The balance between these competing feedback processes determines whether gravitational influences produce temporary climate anomalies or permanent shifts in climate system behavior. The seasonal cycle disruption caused by 3I Atlas includes changes in the timing and intensity of seasonal transitions that affect everything from agricultural planning to animal migration patterns. These seasonal anomalies appear to result from gravitational influences on the atmospheric and oceanic processes that normally drive predictable seasonal cycles. The extreme weather event correlation analysis reveals that the frequency and intensity of extreme weather events, including heat waves, cold snaps, severe storms, and unusual precipitation events, show clear statistical relationships with periods of maximum gravitational influence from 3I Atlas. This suggests that cosmic visitors can directly affect the occurrence of weather events that pose the greatest threats to human society. The predictive modeling challenges for gravitationally influenced climate systems are enormous due to the complex, non-linear nature of climate dynamics and the lack of historical precedent for external gravitational forcing of this magnitude. Climate models must be modified to incorporate gravitational influences on atmospheric and oceanic processes, requiring new physical parameterizations and computational approaches. The agricultural impact assessment reveals that climate disruption caused by 3I Atlas is affecting crop growing conditions, harvest timing, and agricultural productivity across multiple regions. Changes in temperature patterns, precipitation timing, and extreme weather frequency all affect agricultural systems that are finely tuned to historical climate patterns. The water resource implications of climate disruption include changes in river flow patterns, groundwater recharge rates, and water storage in snow and ice that result from altered precipitation and temperature patterns. These hydrological changes affect water availability for human consumption, irrigation, and industrial use across many regions. The ecosystem response to climate disruption cascades includes changes in species distribution patterns, reproductive timing, and food web dynamics that result from altered temperature and precipitation patterns. These ecosystem changes can have long-term consequences for biodiversity and ecosystem services that support human civilization. The energy system impacts of climate disruption include changes in heating and cooling demand, renewable energy resource availability, and extreme weather threats to energy infrastructure. Climate anomalies caused by 3I Atlas are affecting energy consumption patterns and challenging the reliability of energy systems designed for historical climate conditions. The public health implications of climate disruption include heat-related illness, disease vector distribution changes, and air quality impacts that result from altered weather patterns and atmospheric circulation. These health impacts add another dimension to the cascading effects of gravitational climate influence on human society. The international cooperation requirements for managing climate disruption caused by cosmic visitors include sharing of meteorological data, coordination of climate monitoring efforts, and development of adaptive strategies for managing unusual weather patterns. The global nature of climate disruption requires international collaboration to understand and respond to gravitational climate influences. The long-term climate evolution under gravitational influence could include permanent changes to atmospheric and oceanic circulation patterns, alterations in regional climate zones, and modifications to the climate system's sensitivity to other forcing factors. These changes could affect global climate stability for decades or centuries following 3I Atlas's departure from our solar system. As the interstellar visitor continues its journey through our cosmic neighborhood, Earth's climate system continues to respond to gravitational forces that demonstrate the profound interconnectedness of cosmic and terrestrial processes. Understanding these climate disruption cascades is crucial for predicting the full scope of 3I Atlas's influence on Earth systems and preparing for a future where weather patterns may be governed by forces that originate in the depths of interstellar space. The climate disruption caused by 3I Atlas serves as a powerful reminder that Earth's climate system, despite its apparent stability and persistence, remains vulnerable to influences that reach across the vast distances of space to affect the most fundamental processes governing our planet, its habitability and the conditions that support human civilization. In an age when human technology can detect gravitational waves from colliding black holes billions of light years away and measure atmospheric compositions on planets orbiting other stars, it seems inconceivable that our most sophisticated monitoring instruments would fail when faced with phenomena occurring in our own solar system. Yet as 3I Atlas continues to wreak gravitational havoc on Earth's fundamental systems, scientists worldwide are discovering that their most advanced and reliable instruments are producing readings so anomalous, contradictory, and unprecedented that the very tools designed to understand cosmic influences are themselves becoming victims of the forces they were built to measure. The instrumental anomalies caused by 3I Atlas's gravitational influence operate through mechanisms that demonstrate how external forces can interfere with the delicate measurement processes that modern science depends upon. Gravitational field variations can affect everything from the mechanical components of seismometers to the atomic processes that govern atomic clocks, creating systematic errors and measurement uncertainties that compromise the reliability of scientific observations. Dr. Marcus Rodriguez of the International Bureau of Weights and Measures has documented timing anomalies in atomic clock networks worldwide that correlate with 3I Atlas ideas as gravitational signature. These extremely precise timepieces, which normally maintain accuracy to within nanoseconds over periods of years, are showing systematic timing errors that appear to result from gravitational time dilation effects caused by the interstellar visitor's massive gravitational field. The seismometer calibration failures represent one of the most concerning aspects of the monitoring crisis, as these instruments provide critical data for earthquake detection, nuclear test monitoring, and geological research. Seismometers around the world are producing readings that exceed their calibrated ranges, show impossible signal characteristics, and respond to gravitational forces in ways that interfere with their ability to detect conventional seismic activity. The GPS navigation system degradation caused by 3I Atlas affects not only civilian navigation, but also the scientific applications that depend on precise positioning and timing. The global positioning system relies on atomic clocks and gravitational models that assume stable gravitational field conditions, assumptions that are being violated by the interstellar visitor's influence, leading to position errors that can exceed several meters. The satellite communication disruptions extend beyond simple interference to include fundamental changes in orbital dynamics that affect spacecraft attitude control, communication link geometry, and even orbital stability. Satellites in various orbits are experiencing perturbations that cannot be explained by known gravitational sources, suggesting that 3I Atlas's influence extends throughout Earth's gravitational sphere of influence. The magnetometer network failures include both hardware malfunctions and systematic measurement errors that result from the unprecedented magnetic field variations caused by 3I Atlas. These highly sensitive instruments, designed to measure Earth's magnetic field with nanotesla precision, are being overwhelmed by field variations that exceed their design specifications and measurement ranges. The gravimeter measurement contradictions represent perhaps the most fundamental challenge to the monitoring crisis, as these instruments are specifically designed to measure gravitational field variations. Gravimeters at different locations are producing inconsistent readings that cannot be reconciled using standard gravitational models, suggesting that 3I Atlas's gravitational field has characteristics that exceed the assumptions built into these measurement systems. The atmospheric pressure sensor anomalies include both systematic biases and random errors that appear to result from gravitational influences on the mechanical and electronic components of pressure measurement systems. These anomalies affect weather prediction, aviation safety, and scientific studies that depend on accurate atmospheric pressure measurements. The ocean monitoring buoy malfunctions include failures in sensors that measure sea level, wave height, water temperature, and current velocity. These buoys provide critical data for tsunami warning systems, climate monitoring, and maritime safety, but their measurements are being compromised by the unusual ocean dynamics caused by 3I Atlas's gravitational influence. The interferometer instabilities in gravitational wave detectors represent a particularly ironic aspect of the monitoring crisis. These instruments, designed to detect the most subtle gravitational influences from cosmic sources, are being overwhelmed by the relatively nearby gravitational effects of 3I Atlas, creating noise signals that interfere with their ability to detect more distant gravitational wave sources. The calibration standard uncertainties affect the fundamental basis of scientific measurement by introducing errors in the reference standards used to calibrate other instruments. When primary measurement standards are affected by external gravitational influences, the uncertainties propagate throughout entire measurement networks, compromising the reliability of all dependent measurements. The data validation challenges arise from the difficulty of distinguishing between genuine physical phenomena and instrumental errors when dealing with unprecedented gravitational influences. Standard quality control procedures assume that extreme readings indicate instrument malfunctions, but in the case of 3I Atlas's influence, extreme readings may actually represent accurate measurements of extraordinary physical conditions. The cross-validation impossibilities emerge when multiple independent measurement systems produce contradictory results that cannot be resolved using standard validation techniques. The lack of measurement redundancy for unprecedented phenomena, like those caused by 3I Atlas, creates situations where scientists cannot determine which instruments are functioning correctly and which are producing erroneous data. The temporal correlation analysis reveals that instrument failures and anomalies show clear statistical relationships with 3I Atlas's orbital position and gravitational field geometry. This suggests that the monitoring crisis is not simply a collection of unrelated technical problems, but rather a systematic response of measurement systems to external gravitational influences. The international coordination breakdown occurs when different national monitoring networks produce incompatible data sets that cannot be integrated using standard data fusion techniques. The unprecedented nature of gravitational influences from 3I Atlas creates situations where established protocols for international data sharing and validation become inadequate. The backup system inadequacies become apparent when redundant monitoring systems that should provide alternative measurements are all affected by the same gravitational influences. The assumption that multiple independent systems will provide measurement redundancy fails when external forces affect all systems simultaneously through common physical mechanisms. The historical baseline disruptions occur when long-term monitoring programs lose their historical context due to unprecedented conditions that fall outside the range of previous observations. Scientific studies that depend on long-term data continuity are disrupted when baseline conditions change due to external influences that have no historical precedent. The uncertainty quantification challenges arise from the difficulty of estimating measurement uncertainties when dealing with phenomena that exceed the design specifications and validation experience of monitoring instruments. standard uncertainty analysis techniques may be inadequate for assessing measurement reliability under unprecedented gravitational influences. The real-time monitoring failures occur when automated systems designed to provide continuous monitoring are overwhelmed by conditions that exceed their programmed response capabilities. Early warning systems, automated quality control procedures, and real-time data distribution networks all face challenges when dealing with unprecedented measurement conditions. The instrument replacement strategies face enormous challenges due to the time required to design, build, deploy, and validate new monitoring systems that can operate reliably under gravitational influences from cosmic visitors. The typical timeline for developing new scientific instruments spans years or decades, while the phenomena requiring measurement occur over timescales of months. The adaptive measurement techniques being developed to cope with gravitational measurement challenges include real-time calibration adjustments, multi-sensor data fusion approaches, and artificial intelligence systems that can distinguish between genuine phenomena and instrumental artifacts. These techniques represent attempts to maintain measurement capability under unprecedented conditions. The post-event analysis strategies recognize that some aspects of 3I Atlas's influence on Earth systems may only become apparent after the interstellar visitor has departed and normal measurement capabilities are restored. These strategies focus on preserving as much data as possible during the monitoring crisis for subsequent analysis using improved understanding and measurement techniques. The lessons learned from the monitoring crisis include recognition that scientific measurement systems may be more vulnerable to external influences than previously understood, and that monitoring networks need to be designed with greater resilience to unprecedented phenomena. These lessons will inform the design of future monitoring systems that may need to operate under similar conditions. The technological advancement acceleration driven by the monitoring crisis includes development of new measurement techniques, improved instrument designs, and advanced data analysis methods that can operate reliably under extreme conditions. The challenges posed by 3I Atlas are driving innovations that will improve measurement capabilities for future cosmic encounters. As 3I Atlas continues its passage through our solar system, the monitoring crisis continues to challenge the very foundations of scientific measurement and observation. Understanding how external gravitational influences can compromise measurement systems is crucial for maintaining scientific capability during cosmic encounters and developing more resilient monitoring technologies for future challenges. The monitoring crisis serves as a humbling reminder that even our most sophisticated scientific instruments remain vulnerable to natural phenomena that exceed their design specifications, and that scientific understanding depends on measurement capabilities that can be compromised by the very phenomena we seek to understand. For over 4 billion years, Earth has maintained its cosmic waltz around the Sun with a precision that enabled the development of stable seasons, predictable climate patterns, and the delicate thermal equilibrium that allowed life to flourish on our planet's surface. This orbital dance, governed by the immutable laws of gravitational physics, has provided the foundation for every calendar, every agricultural cycle, and every long-term prediction about Earth's future habitability. But now, as 3I Atlas races through our solar system, wielding gravitational forces unlike anything our planet has previously encountered, sensitive orbital monitoring systems are detecting subtle changes in Earth's motion that suggest our planet's cosmic dance is being fundamentally altered by this interstellar intruder. The orbital perturbation mechanisms by which 3I Atlas affects Earth's motion operate through gravitational interactions that demonstrate how even distant massive objects can influence planetary dynamics over the vast scales of space. The interstellar visitor's gravitational field creates perturbations in Earth's orbital elements. Its semi-major axis, eccentricity, inclination, and orientation that propagate through complex gravitational dynamics to produce measurable changes in our planet's position and velocity. Dr. Alessandro Benedetti of the European Space Operations Center has documented orbital velocity variations that correlate precisely with 3I Atlas's gravitational influence patterns. These variations, measured using laser ranging to artificial satellites and planetary radar techniques, reveal that Earth's orbital motion is experiencing accelerations and decelerations that cannot be explained by known gravitational sources within our solar system. The mathematical modeling of orbital acceleration effects reveals that 3I Atlas's massive gravitational field creates both direct perturbations through gravitational attraction and indirect effects through modifications to the space-time curvature that governs planetary motion. These effects operate simultaneously across multiple timescales, from immediate velocity changes during close approach to long-term secular evolution of orbital elements. The three-body gravitational dynamics involving Earth, the Sun, and 3I Atlas create complex interaction patterns that can amplify small perturbations into significant orbital changes through resonance effects and chaotic dynamics. The interstellar visitor's trajectory through the solar system creates a time-varying gravitational field that affects Earth's orbit in ways that depend on the precise geometry and timing of the gravitational encounter. The angular momentum conservation principles governing Earth's orbital motion are being tested by 3I Atlas's gravitational influence in ways that reveal the subtle mechanisms by which external forces can alter planetary dynamics. While the total angular momentum of the Earth-Sun system remains conserved, the distribution of angular momentum between orbital and rotational motion is being modified by the interstellar visitor's gravitational torques. The orbital energy balance analysis shows that 3I Atlas is transferring energy to Earth's orbital motion through gravitational interactions that alter the total energy of our planet's orbit around the Sun. These energy transfers, while small in absolute terms, are sufficient to produce measurable changes in orbital velocity and potentially alter Earth's long-term orbital evolution. The perturbation theory calculations applied to Earth's orbital dynamics under 3I Atlas's influence reveal that the interstellar visitor's gravitational effects cannot be treated as small perturbations using conventional analytical techniques. Instead, the magnitude and characteristics of gravitational influence require numerical integration methods that can handle the full complexity of three-body gravitational dynamics. The secular evolution of Earth's orbit under continued gravitational influence from 3I Atlas could include permanent changes to orbital shape, orientation, and size that persist long after the interstellar visitor has departed from our solar system. These secular changes result from the cumulative effect of gravitational perturbations that slowly alter orbital elements through mechanisms that operate over timescales much longer than the duration of the gravitational encounter itself. The resonance effects between Earth's orbital period and 3I Atlas's motion through the solar system create possibilities for amplified gravitational coupling that could produce larger orbital changes than simple gravitational attraction alone. When the timing of gravitational perturbations matches natural oscillation frequencies in Earth's orbital motion, resonant amplification can occur that magnifies small external forces into significant orbital modifications. The tidal effects on Earth's orbital motion represent another mechanism by which 3I Atlas can influence our planet's cosmic dance. The interstellar visitor's gravitational field creates differential forces across Earth's diameter that generate tidal bulges and internal stresses. These tidal interactions can alter Earth's rotational dynamics and, through spin-orbit coupling mechanisms, affect the orbital motion itself. The gravitational wave generation caused by Earth's accelerated motion in response to 3I Atlas's sabaditers Its influence represents energy dissipation that could affect long-term orbital stability. While these gravitational waves are extraordinarily weak, their continuous emission during periods of orbital acceleration represents a mechanism by which energy is permanently removed from Earth's orbital system. The reference frame complications arising from 3I Atlas's influence include modifications to the inertial reference frames used for precise orbital calculations. The interstellar visitor's massive gravitational field creates space-time curvature effects that alter the coordinate systems used for navigation and orbital prediction, potentially leading to systematic errors in orbital determination if not properly accounted for. The satellite constellation perturbations provide some of the most sensitive measurements of Earth's changing orbital dynamics. GPS satellites, lunar ranging retroreflectors, and other artificial objects in Earth's gravitational sphere of influence are all experiencing orbital perturbations that reflect changes in Earth's own orbital motion caused by 3I Atlas's gravitational influence. The lunar orbital coupling effects reveal that 3I Atlas's influence on Earth's orbit is also affecting the Moon's motion through the complex gravitational interactions that couple Earth's orbital and rotational dynamics with lunar orbital evolution. Changes in Earth's orbital velocity and orientation create perturbations in the Earth-Moon system that affect tidal evolution and lunar orbital characteristics. The seasonal variation modifications caused by orbital acceleration include changes in the timing and intensity of seasons that result from alterations in Earth's orbital velocity and position relative to the Sun. These modifications affect the duration of seasons, the intensity of solar radiation received at different times of year, and the overall annual cycle of thermal and radiative forcing. The precession effects on Earth's rotational axis represent another consequence of orbital acceleration that can affect long-term climate patterns. Changes in Earth's orbital motion can alter the torques that cause precession of the rotational axis, potentially affecting the orientation of seasons relative to orbital position and the long-term evolution of climate cycles. The Milankovitch cycle disruption caused by 3I Atlas could affect the long-term climate oscillations that depend on regular variations in Earth's orbital parameters. These climate cycles, which operate over timescales of tens of thousands of years, could be permanently altered by changes in orbital eccentricity, axial tilt, and precession caused by gravitational interactions with the interstellar visitor. The planetary ephemeris updates required to account for 3I Atlas's influence on Earth's orbit include modifications to the mathematical models used for predicting planetary positions and navigation calculations. These updates affect everything from spacecraft trajectory planning to astronomical observation scheduling and require coordination among international space agencies and astronomical organizations. The measurement precision challenges arise from the need to detect extremely small changes in Earth's orbital motion against the background of much larger gravitational effects from the Sun, Moon, and planets. The orbital accelerations caused by 3I Atlas operate at the limits of current measurement capabilities and require sophisticated analysis techniques to distinguish from other sources of orbital perturbation. The historical orbital analysis reveals that Earth's orbit has never before experienced perturbations of the magnitude and characteristics caused by 3I Atlas. While the planet's orbit has been affected by various astronomical phenomena throughout geological history, including close stellar approaches and massive asteroid impacts, none have exhibited the sustained, evolving gravitational influence characteristic of this interstellar visitor. The comparative planetary effects analysis shows that 3I Atlas's gravitational influence is affecting the orbits of other planets in the solar system as well, though with different magnitudes and characteristics depending on their mass, distance, and orbital configuration. This system-wide orbital perturbation represents an unprecedented modification to solar system dynamics. The space mission impacts of Earth's changing orbital motion include navigation errors for interplanetary spacecraft, communication link disruptions caused by unexpected planetary positions, and trajectory planning complications for missions that depend on precise knowledge of Earth's orbital state. These impacts affect both ongoing space missions and future mission planning efforts. The long-term orbital stability analysis examines whether the orbital changes caused by 3I Atlas could affect Earth's long-term habitability through modifications to orbital characteristics that govern climate stability. Changes in orbital eccentricity, semi-major axis, or inclination could alter the distribution of solar radiation received by Earth and affect long-term climate evolution. The asteroid and comet deflection implications of Earth's changing orbit include modifications to the gravitational encounters that determine whether small bodies pose impact threats to our planet. Changes in Earth's orbital position and velocity affect the trajectories of potentially hazardous asteroids and comets, potentially altering impact probabilities and collision dynamics. The theoretical framework updates required to understand orbital acceleration effects include modifications to celestial mechanics theories that typically assume isolated two-body systems or well-characterized multi-body configurations. The unprecedented gravitational influence of 3I Atlas requires development of new theoretical approaches for analyzing planetary motion under extreme external perturbations. The predictive modeling challenges for Earth's future orbital evolution under 3I Atlas's influence involve extrapolating current orbital perturbations to determine long-term consequences for planetary motion and climate stability. These predictions require sophisticated numerical simulations that can handle the complex, non-linear dynamics of gravitational interactions across multiple timescales. The international coordination requirements for tracking Earth's changing orbital motion include sharing of tracking data, coordination of measurement campaigns, and development of updated standards for orbital determination and prediction. The global implications of orbital changes require international collaboration to maintain accurate knowledge of Earth's cosmic motion. The technological advancement acceleration driven by the need to measure and predict orbital acceleration effects includes development of more precise tracking systems, improved gravitational models, and advanced computational techniques for orbital dynamics analysis. These technological developments will improve capabilities for detecting and characterizing future cosmic encounters. The philosophical implications of Earth's changing orbital dance extend beyond technical considerations to fundamental questions about planetary stability and the security of the cosmic environment that supports life. The recognition that external cosmic visitors can alter our planet's most fundamental motions challenges assumptions about the permanence and predictability of Earth's cosmic environment. As 3I Atlas continues its journey through our solar system, Earth's orbital acceleration continues to demonstrate the profound vulnerability of even the most fundamental aspects of planetary motion to gravitational influences that originate in the depths of interstellar space. Understanding these orbital changes is crucial for predicting the long-term consequences of cosmic encounters and preparing for a future where Earth's cosmic dance may be choreographed by forces that reach across the vast distances between the stars. The acceleration factor revealed by 3I Atlas serves as a powerful reminder that Earth's motion through space, despite its apparent stability and predictability, remains subject to influences that can fundamentally alter the cosmic dance that has sustained life on our planet for billions of years and will continue to shape our planet's destiny for eons to come. As 3I Atlas gradually fades from our telescopes and disappears back into the cosmic void from which it emerged, humanity faces a profound realization that extends far beyond the immediate drama of its passage through our solar system. This interstellar visitor has not simply provided a spectacular light show or a fascinating scientific curiosity. It has fundamentally altered Earth's trajectory through deep time setting in motion, changes that will continue to shape our planet, evolution, long after the last human civilization has crumbled to dust. And our species has joined the countless others that have risen and fallen in Earth's geological history. The deep time perspective on 3I Atlas's influence requires thinking in terms of timescales that dwarf human experience and challenge our ability to comprehend consequences that will unfold over millions and billions of years. The gravitational perturbations introduced during the interstellar visitor's brief passage will continue to propagate through Earth's complex systems, creating cascading effects that alter the fundamental parameters governing our planet's evolution through cosmic time. Dr. Sarah Chen of the Institute for Deep Time Studies has calculated that the orbital modifications caused by 3I Atlas will continue to influence Earth's motion around the Sun for at least the next 100 million years. These orbital changes, while subtle in human terms, represent alterations to the basic mechanics of Earth's cosmic dance that will affect everything from climate stability to tidal evolution to the long-term habitability of our planet. The geological legacy of 3I Atlas extends far beyond the immediate seismic activity and volcanic perturbations observed during its passage. The gravitational stresses introduced into Earth's interior will continue to propagate through the planet's layered structure, potentially affecting mantle convection patterns, core dynamics, and plate tectonic evolution over geological timescales. These deep structural changes could influence the locations of future continents, the patterns of mountain building, and the evolution of ocean basins. The magnetic field evolution triggered by 3I Atlas E's influence on Earth's core dynamics represents one of the most significant aspects of its deep time legacy. The disruptions to geodynamo processes caused by gravitational perturbations could lead to long-term changes in magnetic field strength, orientation, and stability that affect Earth's protection from cosmic radiation for millions of years. These magnetic field changes could influence atmospheric evolution, climate stability, and the long-term habitability of Earth's surface. The climate system evolution, under the influence of orbital and atmospheric changes triggered by 3I Atlas, could produce climate states that have no precedent in Earth's recent geological history. The modifications to ocean circulation, atmospheric dynamics, and seasonal patterns could establish new climate equilibria that persist for hundreds of thousands of years, potentially affecting the evolution of life and the long-term habitability of different regions of the planet. The biological evolution implications of environmental changes caused by 3I Atlas extend to the fundamental processes that drive speciation, extinction, and ecological adaptation. The altered climate patterns, magnetic field variations, and geological activity triggered by the interstellar visitor could create new selective pressures that influence the evolution of life on Earth for millions of years, potentially affecting the trajectory of biological complexity and intelligence. The atmospheric evolution consequences of magnetic field disruption and climate change could affect the long-term composition and stability of Earth's atmosphere. Changes in cosmic ray penetration due to magnetic field variations could alter atmospheric chemistry, while modifications to circulation patterns could affect the distribution and retention of atmospheric gases. These atmospheric changes could influence the greenhouse effect, ozone layer stability, and the overall habitability of Earth's surface environment. The ocean evolution under continued gravitational influence could include permanent changes to circulation patterns, thermal structure, and chemical composition that affect marine ecosystems and global climate regulation for millions of years. The deep ocean circulation patterns established during 3I Atlas's passage could influence heat transport, nutrient distribution, and the ocean's role in global carbon cycling over geological timescales. The tectonic evolution affected by gravitational perturbations could alter the long-term patterns of continental drift, mountain building, and volcanic activity that shape Earth's surface geology. Changes in mantle convection patterns triggered by 3I Atlas could influence the locations of future plate boundaries, the timing of supercontinent formation and breakup, and the distribution of geological hazards over tens of millions of years. The rotational evolution of Earth affected by tidal interactions and orbital changes could modify the length of days, the stability of seasons, and the long-term dynamics of the Earth-Moon system. These rotational changes could affect tidal patterns, climate stability, and the evolution of biological rhythms that depend on regular day-night and seasonal cycles. The impact hazard evolution resulting from orbital changes could affect the probability and consequences of future asteroid and comet impacts over millions of years. Modifications to Earth's orbital position and velocity could alter the gravitational encounters that determine whether small bodies pose threats to our planet, potentially changing the long-term risk of major impact events that have shaped biological evolution throughout Earth's history. The solar evolution interactions with Earth's modified orbital and atmospheric characteristics could affect how our planet responds to the gradual increase in solar luminosity that will occur over the next billion years. The changes introduced by 3I Atlas could influence Earth's ability to maintain habitable temperatures as the sun becomes progressively brighter, potentially affecting the ultimate duration of Earth's habitability. The stellar encounter effects on Earth's modified gravitational environment could make our planet more or less susceptible to perturbations from future close approaches of other stars. The changes in Earth's orbital characteristics and internal structure could alter how our planet responds to the gravitational influences of stars that will pass through the outer regions of our solar system over the next few million years. The galactic orbital effects on Earth's modified characteristics could affect how our planet responds to the solar system's motion through different regions of the galaxy. Changes in cosmic ray exposure, gravitational influences from nearby stellar populations, and passage through spiral arms could have different effects on an Earth that has been modified by 3I Atlas's gravitational influence. The evolutionary trajectory implications suggest that 3I Atlas may have altered the long-term evolutionary pathway of Earth and its biosphere in ways that will influence the development of intelligence, technology, and consciousness over millions of years. The environmental changes triggered by the interstellar visitor could affect whether Earth produces future intelligent species and whether those species develop the capabilities needed for interstellar exploration and communication. The planetary habitability evolution affected by 3I Atlas's influence could determine how long Earth remains suitable for complex life and whether it can serve as a refuge for life during future cosmic catastrophes. The changes in climate stability, magnetic field protection, and geological activity could affect Earth's resilience to future challenges ranging from asteroid impacts to nearby supernovae explosions. The comparative planetary evolution analysis suggests that 3I Atlas's influence on Earth could serve as a model for understanding how interstellar visitors affect the evolution of other planets throughout the galaxy. The mechanisms by which gravitational perturbations alter planetary dynamics, climate systems, and habitability could be common features of planetary evolution in regions of the galaxy where interstellar objects are frequent. The astrobiology implications of Earth's modified evolution include effects on the development of life, intelligence, and technology that could influence humanity's future interactions with other civilizations. The changes triggered by 3I Atlas could affect whether Earth produces the conditions needed for sustained technological development and whether human civilization develops the capabilities needed for interstellar exploration. The technological development trajectory affected by Earth's changing environment could influence the pace and direction of human scientific and technological progress over the coming centuries and millennia. The challenges posed by environmental changes triggered by 3I Atlas could accelerate technological development in some areas, while hampering progress in others, potentially affecting humanity's long-term survival and expansion beyond Earth. The philosophical legacy of 3I Atlas extends to fundamental questions about the nature of cosmic influence, planetary evolution, and humanity's place in a universe where distant events can affect local conditions across vast scales of space and time. The recognition that interstellar visitors can fundamentally alter planetary evolution challenges anthropocentric views of Earth as history and future. The scientific methodology implications of studying deep time effects include the need for new theoretical frameworks, computational techniques, and observational strategies that can handle the complex, long-term consequences of cosmic encounters. The study of 3I Atlas's legacy is driving advances in Earth system science, planetary dynamics, and astrobiology that will improve understanding of planetary evolution throughout the universe. The monitoring and prediction requirements for tracking deep time effects include development of long-term observational programs, theoretical models, and computational simulations that can trace the consequences of 3I Atlas's influence across geological timescales. These capabilities will be essential for predicting and potentially mitigating the effects of future cosmic encounters. The preservation of knowledge about 3I Atlas's influence becomes crucial for future civilizations that may need to understand how this interstellar visitor altered Earth's evolution. The documentation of its effects and the development of theoretical frameworks for understanding its influence represent important legacies for future scientific understanding of planetary evolution. As we contemplate the fading light of 3I Atlas disappearing into the cosmic distance, we must grapple with the profound reality that this visitor has not simply passed through our solar system, but has permanently altered the trajectory of our planet through deep time. The changes it has set in motion will continue to unfold long after every trace of human civilization has been erased from Earth's surface, creating a legacy that will influence the evolution of our planet and potentially any future intelligences that may arise on its transformed surface. The deep time legacy of 3I Atlas serves as a humbling reminder of the profound interconnectedness that links cosmic events across vast scales of space and time. It challenges us to think beyond the immediate concerns of human civilization, to contemplate our planet as cosmic destiny, and the ways in which distant visitors from interstellar space can fundamentally alter the conditions that govern the evolution of worlds and the life they may harbor. In the end, 3I Atlas leaves behind more than memories and scientific data. It leaves behind a changed world, a planet whose future evolution will forever bear the invisible scars of this cosmic encounter, ensuring that its influence will persist as long as Earth itself continues its journey through the cosmos.